All right, cool. Hi, everyone. I'll get going then. Thank you. It's such a pleasure to be here, being able to talk about what we've been doing at Aztec with you all, which is confidential digital assets on Ethereum. We are a privacy solution for the Ethereum mainnet that enables developers and individuals to create private digital assets, confidential digital assets, and confidential zero-knowledge dApps that interact with these assets, just like you within the ERC20 token. At least that's the vision. So I was going to go quickly over what I'm going to try to achieve in this talk, which is kind of explaining what we think needs to happen to actually put confidential transactions to work on Ethereum.
Who you are, what you do, and
Wait, I didn't do that, did I? I'm Zach. I'm the CTO of Aztec. We're a team based in London that are focused around building this privacy solution for Ethereum as a protocol layer for L1. Fundamentally, what we believe is that Ethereum and public blockchains in general can't really achieve their true potential unless you can represent value on layer 1 confidentially. If the fundamental representation of value is private, then it opens up an enormous number of potential use cases that currently can't be explored. Like almost all of traditional finance and traditional financial services kind of require privacy by default. Which is one of the reasons why you don't see a large proliferation of things like mortgages, corporate bonds, syndicated loans on blockchain. One of the key blockers is privacy, and we're trying to solve that in a generic capacity. So for the agenda, what on earth needs to happen for that to actually be a reality? How do we get an L1 solution that enables individuals, users, developers to create private digital assets without having to be literate in zero-knowledge cryptography? And that feeds into the cryptography engine standard, what the hell that is, because that helps us achieve that, how we create our efficient range proofs, and then finally going into a little bit about our confidential token standard and the roadmap and what you can do to actually start to develop with these things. So before I go ahead, how many people here are interested in creating private tokens, private assets on Ethereum, or dApps zero-knowledge dApps that interact with private assets? Right, how many people have actually done so? Yeah, here's the problem. So this stuff is hard, really damn hard, for a lot of reasons. You have to handle a proliferation of secret keys usually. It's very hard to create these application-specific proofs. You need to be quite literate in zkSummit or zkSummit or Sigma protocols or zero-knowledge crypto. There's no standardization, so if you make a solution, it's not going to be compatible with other people's solutions. You've got to deal with trusted setup sometimes, and then you have to deal with long, hard, and difficult proof constructions, which present a massive UX challenge for a browser-based app, and expensive proof verification, which is expensive. How do we bridge the gap between the technical vision and reality? How do we make this stuff actually workable? So step 1, what do we want? What do we actually want? We need to, because zero-knowledge proofs can be used for a lot of things. And so they have a habit of getting conflated a lot, but they are quite distinct and they need their own solutions. Private transaction scaling solutions, publicly verifiable private computation, they're all extremely important for fully developing the Ethereum ecosystem, for blockchain ecosystems. What we at Aztec are focusing on is that confidential transactions layer, being able to represent the fundamental unit of value on layer 1 privately in an encrypted way, being able to transfer it, having a common standard so that this is can be applied universally. So the building blocks for a confidential ecosystem are, in my opinion, what you need customizable confidential transaction semantics. If you're building an application-specific sidechain, it's absolutely fine to do batch validation of transactions. You can process 10,000 transactions on the sidechain as a batch, use zkSNARK or zkStark proof to validate the correctness of that computation. However, for actual the fundamental representation of value, the actual digital asset itself, you have edge cases. You always have edge cases in the real world where the actual specific semantics of your transaction are different. One example would be if for regulatory reasons you need to make sure that no trader has more than 10% of the supply of your private asset, or if you have some kind of minimum trade threshold, or you have some kind of compliance group signature scheme you need to prove that you've been KYC'd anonymously. And so you need individuality. However, you also need interoperability. So these are somewhat orthogonal to one another. You need to be able to have confidential assets, private assets that all conform to a common standard, like ERC20, so that you can actually communicate. They can communicate with one another. You can transfer tokens and zero-knowledge notes to and from these assets via smart contracts. You can actually start to create meaningful dApp ecosystems. And also for that, you need a single common reference string. Basically, you can't have multiple trusted setups because then, as a dApp builder, you need to make like an opinionated guess at which assets and dApps you have trusted setups that you trust and which ones don't. If everyone just uses one trusted setup, well, I mean, ideally 0, but just one, then you get rid of that problem. And obviously, you need developer-friendly tools. Like right now, these are mostly completely absent, not due to a lack of ambition or talent, but just because there's hardly any resources in this space. And right now, the tooling is extremely difficult to use, even for people that are quite proficient in this stuff. And then finally, you need efficient proof construction and verification. On the proof side, for good UX, if you're building a dApp in the browser and you need to construct zero-knowledge proofs, you don't want that to take 2 minutes. And you want it to be able to be done on hardware wallets. And for verification, obviously, gas is money, and it needs to be cheap. So how do we forge these building blocks? First of all, a family of zero-knowledge proofs that share this common reference string. Basically, define a set of proofs that individually perform certain kind of discrete parts of business logic. Like, for example, an interest rate proof. So like you can prove like this value is X% of this value. Or a basic join split transaction, which I'll go to in a minute. But basically have these kind of a modular proof system where you can kind of pick and choose proofs off the shelf to define the specific semantics of your individual asset. And a shared suite of validation contracts, so we're calling the cryptography engine. This is extremely important, and I'll get to that in the next slide. But one of the things you can do with this is it means you abstract away the zero-knowledge validation part from the smart contract you're building. You can use somebody else's libraries, somebody who's experienced in this stuff that actually that has a lot of technical expertise. And it means that these assets are forward compatible. Because if you have a digital asset, a private asset that subscribes to the cryptography engine, then if that cryptography engine adds new proofs over time that do more interesting and innovative things, your asset, if you choose to be, will be automatically forward compatible with those new proofs, which is obviously quite valuable. Specifically, as this industry is changing so much, probably in 5 years' time, we'll have an enormous plethora of zero-knowledge technologies that we don't have at the moment, and it would be very nice if the assets built today are forwards compatible with those. And then finally, you need a confidential token standard to tie this all together. So a way of building a confidential asset that has a common interface, a common standard, so that you can have interoperability and compatibility. And then finally, some really good dev tools that abstract away all the nitty-gritty of actually making zero-knowledge proofs. Just in the same way you can do web3.eth.sign transaction, that makes a new DSA signature. You don't need to know about the mechanics of how that actually happens. You just need to know that you need a private key and a message. So I want to go into how you transfer value privately on Ethereum, at least how we do it, which is through these balancing relationships formed out of join split statements. So these are not these have been around for a while. I think Zcash originally pioneered them. Where basically you just have some input notes. Notes are like Uxter objects on Bitcoin, except the values are encrypted. And you prove that the sum of the values of your input notes is equal to the sum of the values of your output notes. And then if you serve this proof, you prove this successfully, then a smart contract can destroy the input notes in its state registry and create the output notes. And that smart contract knows that you've not double spent, but it has absolutely no idea about what's inside those notes, which is, of course, the whole point. And then one extra addition is, sorry, 1 second, is if there is a deficit in this balancing relationship, you can fill up that deficit with public tokens. So imagine your output notes are worth 20 and your input notes are worth 10. That means you want to extract 10 more value than you put in. And so if you make that shortfall in tokens, then you're basically converting 10 tokens into a zero-knowledge note form. And that's how you get value into and out of our crypto system. On-chain, notes are public. So the existence of a note is public and the owner of a note is public. This was a deliberate design decision to improve compatibility between different private assets. We have a stealth address protocol that can be used to make that the owner of a note is completely meaningless, but the existence of a note is there. And then the private data is its value, and then you have a viewing key and a spending key. We kept these keys deliberately distinct. You need the viewing key to construct the zero-knowledge proofs and decrypt the note, and you need the spending key to actually authorize transfers of value, which is valuable because that means then you can give viewing keys to relayers. You can then construct proofs on your behalf, but you can very strictly define what those proofs can produce through signing with your spending key. And this really helps for extremely, much more complicated, zero-knowledge protocols where having a relay in the mix would really help if there is that kind of entity that you would trust with a viewing key. So to put it all together, this is an example of a bilateral swap using the Aztec protocol, EIC 1723 and 1724 standards. I'm going to try and go through this. This is from our protocol specification, which is in its draft release. There's a link to it later. Basically, what this is a bilateral exchange of encrypted value between two digital assets that have no knowledge of each other's existence. Effectively, the caller will have a proof, will have a valid zero-knowledge proof of a bilateral swap between these notes. Basically, two actors are trading notes from two different assets. And we have a zkDApp. So imagine this is an exchange DApp that actually its job is to perform these swaps, to process orders. What this thing will do is it'll talk to the cryptography engine, the Aztec cryptography engine, ACE, to validate this bilateral swap proof. Once validated, the cryptography engine will spit out two transfer instructions. And this is one of the key things about the cryptography engine is it takes abstract, arcane zero-knowledge proofs as inputs, and it spits out transfer instructions as outputs that conform to a common standard. So now, once that zkDApp has its two transfer instructions, which say, destroy these notes, make these notes, what it can do is it can then send those transfer instructions to the relative zero-knowledge assets. And now, what happens when a zero-knowledge asset receives this transfer instruction? Well, it has absolutely no idea about that DApp. It doesn't know what it is. It could be a smart contract. It could be a person. It could be somebody tapping Morse code into a TCP/IP connection to manipulate a blockchain node. It has no idea. But it does know about the cryptography engine. It's subscribed to that. So it can query the cryptography engine and go, hey, I've received this instruction. Is this a valid instruction? Where did this come from? And the cryptography engine go, yes, actually, that instruction satisfies a balancing relationship from a bilateral swap proof. And it can do that just automatically because it validated that proof previously. And this is the real strength of the system because it means that both these two zk assets, they don't need to validate their own zero-knowledge proofs because it's already happened in the bilateral swap proof. Normally, traditionally, all one of these assets would have to validate a zero-knowledge proof according to their own custom individual semantics, which would mean 3 zero-knowledge proofs, which would be ridiculously expensive. But with this one, you only need one because they're all listening to the same cryptography engine. That cryptography engine will then, once it's affirmed that a balancing relationship holds, that asset then can then do its own permissioning checks. Do we have the right signatures? Do we have the right approvals? Blah, blah, blah. And then it can issue the transfer instruction back to the cryptography engine, which will update the relevant note registry, destroying and creating the relevant notes. The reason why the cryptography engine controls the note registry instead of the asset is because that means the cryptography engine can provide a cast iron guarantee of the correctness of the state of every note registry, that there has been no double spending in any note registry, that the only way to add or change or manipulate notes is through balancing relationships. This is extremely important in the long term because it means that you can denominate one zero-knowledge asset as a percentage of another note of another asset. You can say these notes are worth X% of the notes in this note registry, and you know that because the second note registry has no double spending, that's a legitimate thing you can do. This is a bit abstract. I can talk about it after in questions, but that's one of the fundamental reasons why we can do dividend payments, interest rate payments through Aztec, percentage payments in zero knowledge. And then once that's all done, control flow will feed back down to the zkDApp. I know this might look a bit complicated, and that's because it is. This is a multilateral transfer of encrypted value being mediated and validated by a public blockchain. But the thing is, this exists, it works, and it's practical. This entire flow will run you about, at the moment, 750,000 gas. And when some ERPs come on stream, that cost will get crushed down. And compared to more to other kinds of zero-knowledge proving technologies, if everything had its own protocols, its own zero-knowledge proof semantics, this type of flow would blow through the block gas limit quite easily. So I did mention that efficient range proof. The whole reason why these zero-knowledge proofs can happen, this system can happen, is because we have our zero-knowledge protocols are efficient to verify because of this range proof. So I want to see, I don't have a lot of time, but I'm going to try and go into it a little bit, if that's all right. Because this is, after all, the Zero-Knowledge Cryptography Conference. Our range proof is built on fundamentally a polynomial commitment scheme. Normally, polynomial commitment schemes are extremely powerful in zero-knowledge cryptography because it means you can very efficiently prove very complicated relationships. Specifically, the thing about polynomials, when expressed over a finite field, so like a group of integers modulo a large prime, and evaluated in an elliptic curve is for two scalars in this finite field, the difference between the scalars will perfectly divide the difference between that polynomial evaluated at those two scalars. That seems a bit abstract. Like, what's the point? Well, it means that if you take this relationship, let's call it nu, you can always compute this. Even if y is a secret created during the trusted setup, even if you do not know what y is, you can still compute the coefficients of the polynomial that is required. And then when expressed over an elliptic curve, if you're given the correct points, you can then reconstruct the polynomial over an elliptic curve and prove that, yes, you have a commitment to the polynomial. This is valuable because what if you construct your polynomial so that if you commit to an integer which is within the range of your range proof, it evaluates to 0. This is really important because then you get this relationship. Now nu becomes this, just this expression, polynomial evaluated over y divided by 1 minus k. And so when you juggle the math and rearrange it, you get to this equation, and you can express this over an elliptic curve using bilinear pairings. So I'm using exponential notation. G is the generator in the first group. G2 is the generator in the second, like larger pairing group. So you can just multiply these together. Basically, nu times y equals the polynomial evaluated at y multiplied by nu times k. Why is this important? Because if you satisfy that relationship, then you committed to that polynomial where the evaluated polynomial is 0. Because otherwise, if it wasn't 0, you'd have an extra term in here. That isn't there. And you can construct your crypto system so that it is impossible to sneak that term in. And I'll get into that in a little bit. So trusted setup. I mentioned trusted setup. We do have a trusted setup. You have to basically evaluate that polynomial over a secret y that nobody knows. This is extremely similar to zkSummit powers of tau ceremony, to the point where we can actually use phase 1 of zkSummit powers of tau ceremony. So you have these powers, and then you can use those powers to construct these polynomial equations expressed over an elliptic curve. Basically, you can very efficiently figure out the coefficients of these polynomials and compute them. Phi expressed over y, and then what you can do is you can take this divided by this. You can efficiently compute the polynomial coefficients for that and compute those polynomials. Why is that important? Because now, if you select, imagine that's in a database, because it is. If you select one of these new values and you check that if you multiply this by k and then add it to the polynomial expressed over y. Sorry, I'm going to flip this around. If this is equal to the base point you picked from your database, paired with the trusted setup public key, like G2 to the y, if these match, then you have a commitment to an integer where that integer is in the valid range of the range proof. And you cannot satisfy that equation without that being the case, unless A, you know why, or B, you've solved one of the discrete logarithm problems that so much of elliptic curve cryptography is based around. To kind of get to the end of this, how do you actually use that to make a commitment function? How do I commit to an integer in a way that it means it's encrypted, and it has the cryptographic properties of being computationally binding, which means if I commit to an integer, when I open the commitment, I can only open it to that integer. I can't open it to something else. And information theoretic hiding, which means that if I give somebody my commitment, they can't figure out what I've committed to. They can't figure out what the integer is. Well, first of all, we need some randomness, obviously, because you need to randomize this stuff. But then what you do is you just pick the trusted, if you want to commit to an integer, you pick the relevant point out of the trusted setup database, multiply it by that randomness A. That's one of your points, gamma. Sigma is then gamma multiplied by k, added together with h, which is the polynomial evaluated over y, multiplied by a. And if you expand all of that out, which I don't have time for, I'm afraid, into these pairing equations, you get back to that polynomial commitment function. And this can be treated like a predicate commitment. H can be treated like a generator because it has a factor of y in it, which means that you cannot map between gamma and h, or h and sigma, or h and the generator point g, because every single one of those mappings has a coefficient of y in it. And you don't know what y is, because it was just ideally destroyed during the trusted setup. And that's how we get an extremely efficient range proof. Our range proof, all you have to do is step 1, use the Sigma protocol to prove in zero knowledge that you can open a Aztec commitment. And then step 2 is just do this bilinear pairing check. So if you consider a Sigma protocol that opens a Pedersen commitment, the only difference is this bilinear pairing check. And one of the extra strengths of the Aztec protocol is the right-hand side of these pairing equations. Those arguments, they're constant. And they're always constant for every single Aztec node, which means if you have multiple Aztec nodes in a proof, you can create a linear combination of the Aztec commitments, each multiplied by a random variable, and then use that in one pairing check. Basically, you can condense an arbitrary number of Aztec range proofs down to one pairing check and a Sigma protocol to to prove you can open the Aztec node, which is extremely powerful because pairings are expensive. So you can use this in conjunction with Sigma protocols to prove algebraic relationships directly expressed in the kind of exponent of an elliptic curve, and that's what we use for our join split, balancing relationships, bilateral swap, interest rate payments, blah, blah, blah. And you can expand this to create quite reasonably expressive proof statements. There is a limit to how far you can go, but there is always this compromise between interoperability and customizability. The more custom you get, the less interoperable you get. So we've tried to find a balance between the two. So this is our cryptography engine standard. These are the proofs that are in kind of our V version 1.0. So you have that bilateral swap join split. We have a partial order filling proof on the way we'll get to that if people request it. We're focusing more on our tooling at the moment. And then some utility proofs for those customizable transaction semantics. And right now, today, those are the gas costs, which seem, they're not, it is 800,000 gas, but sorry, this is a tautology. It's 800,000 gas. This is actually practical. You can do this today, and sure, it'll run you 30 cents, but my God, it's actually possible. You can actually create today confidential digital assets using the Aztec protocol and have them and actually have confidential settlements between different kinds of private assets, which is not something which has really been talked about much. But I think one of the key strengths of Ethereum is that it is a settlements layer, and once you have private settlements, then that opens up an enormous spectrum of use cases which can't currently exist. And then commenting finally also with our ER1724, our confidential token standard. So this interface looks ideally quite similar to an ERC20. It has confidential approve and confidential transfer from. But the idea is we extract away all the cryptography into these kind of these bytes Aztec proof variables. Basically, you use our Aztec proof construction APIs to say, make me a proof. Here are the input notes that I have, and here are the output notes I want. Boom, you get your proof. You can just feed it into the smart contract. You don't need to deal with the fuzzy mechanics of what's happening inside. And then this is all culminating in our Aztec monorepo. So this is where all our code is. This is where the guts of Aztec is. And if you want to play around with Aztec, start working on building confidential assets, this is where to go. Aztec.js is our proof construction library. Protocol contains our smart contract templates for our cryptography engine and example ER1724 contracts. And if you want to get your hands stuck in with developing private assets, well, me and my colleague Paul, we're here today. So if you really want to ask us any questions, please by all means do so. Paul also wrote an example in our Medium publication of how to get started with Aztec, how to make a confidential digital asset. And this morning we published our draft specification of our V1.0 protocol at our GitHub repository. So those are the places to go if you want to start looking into Aztec. Finally, because I'm almost out of time, the roadmap for Aztec 1.0. So end of Q1, which is about now, but we're a couple of days behind track because we've pushed our security order forward. MVP and cryptography engine deployed the testnets, our complete proof construction API, and this kind of optimized elliptic curve smart contract, something called VS-Strudel. Basically, it does what one of the precompiles does, but a little bit faster. Get that deployed to cut our costs down by 20%. Q2, finish our trusted setup, our multi-party computation. We can collaborate with the people who also need this. People using zkSummit on Ethereum, they need to do exactly the same trusted setup as us. So there's an enormous scope for collaboration there. And then formal verification over actual smart contracts and cryptography engine. Because my God, if there was ever a need for formal verification, it is when you're validating bespoke, custom, zero-knowledge cryptography. And so we intend to do that. But I should also add, all our cryptographic protocols, we have formal soundness proofs for them. So mathematically, they are completely secure as long as you can trust discrete logarithm assumptions. Yeah, and so we just wanted to make sure that the code is an expression of the mathematics. And then Q3, release our production-grade mainnet release. Well, thank you very much. I've been Zach, and it's been a real pleasure. Thank you. Yep. Beep. Yes. So the user needs to have an exchange of notes. So basically they have to, like an order maker and order taker, they both have notes they want and notes they need. At the moment, our bilateral swap proof does use a relayer for efficiency reasons, but we also have we've a bit constrained on resources, but we also have like another proof which doesn't require the relay, which is just a bit more expensive. And so we're definitely getting that into our mainnet production release, where basically you have two users. They both say, here's a note I want, here's a note I need, here's the zero knowledge proof to do the transfer. Both users do that their side of the proof, and then the cryptography engine kind of like validates them both in a batch, which is a bit more efficient than doing them individually. And that will then spit out the swap orders.
Is effectively the relay being used to keep them confidential? Because otherwise, how would they
Yeah, so the relay would be, absolutely, the relay would be trusted with the viewing keys and trusted with not like splurging the viewing keys and revealing like who owns notes and what they're worth.
But is it possible to match files and stuff without having
Yes, it is possible with the multi-party computation protocol, which we've not really explored at the moment just because it's quite gas intensive and it's quite like the UX is really bad because you basically have two users that have to like kind of eke ever closer towards like matching. Me, I might have an order for 58, maybe I have an order for 48. What do you have? And going through successive rounds is an absolute pain in the neck. So I mean, if there's demand for it, we'll build it absolutely. But right now we're focusing on more simpler primitives.
Do the maker and taker have to interact in any way, shape, or form with each other? Or no?
Once an order's matched, no. No, they don't. They basically either two ways. One, they use the kind of like exactly. What you do in that situation, you construct a digital signature saying, I want to sell like this. I want to sell 10 for like at this price, and here's the viewing key. So then what the relay would do, once they've matched the proof, they construct the zero knowledge proof. But then the smart contract would check the signatures and check, hey, is the output of this proof equal to what these signatures asked for? And that's how. So yeah, it's complete from the order creator, order taker, maker's perspective. It's completely non-interactive once they've given that data to the relay.
So does the maker have to do something else if they offer, like, want to sell 20, but they only sell 10? Do they have to do something?
Now that's where my partial order filling zero knowledge proof comes in. But it's, we've just been a bit too busy with the core protocol stuff. But that's definitely going in the engine because like partial order filling, it can be done. I think it's really cool, and it's important. Yeah. Cool. Right. Like one last question.
Yeah,
okay.
How does this batch validation work? So how does this get triggered, and where does it happen?
So do you mean with when I talked earlier about like that would be a specific actual zero knowledge proof like type. So the idea is you can add different proofs to the cryptography engine. They all have like an identifier which describes what they do. And what you'd add one, basically every single zero knowledge proof has its own validator smart contract. So you'd add one that actually validates Aztec proofs in a batch, and that's how you'd process it.
And then people provide to the cryptographic engine their proofs, and then in a bunch they get validated.
So yeah, what you have to do is you'd have to have people like either somebody or a smart contract accumulate a bunch of proofs. And then go to the cryptography engine and go, here's the input to this proof ID, this batch validation proof, please validate it.
Who's doing this call?
Pardon?
Who's doing this call to?
So that's very context dependent, isn't it? Like for two people doing a trade, either them or a coordinator, a relayer type person would be validating the batch. I do want to just narrow down what I mean by batch. This is not, as it currently stands, a scaling solution. Batch validation, it is more efficient than validating individual Aztec proofs, but it still does grow linearly. So it's small batches only more for like UX convenience and a slight gas optimization than any kind of scaling solution. Yeah. Cool. Well, thank you very much. It's been a pleasure.